Each night, a fixed canopy of lights circles the Earth. Yet, over time, some of these lights seem to wander, shifting their positions among the stars. Our ancestors called them planets and believed they shaped the fate of humanity. Those who could predict their motions held special influence with kings and princes. But prediction requires knowledge. How do the planets move, and why? These questions mark the beginning of modern astronomy, a journey of discovery that uncovered the true nature of planetary motion and led to a better understanding of our place in the cosmos.
In my view, the ancient Greeks invented astronomy. Other people, of course, had observed celestial bodies and the heavens, but they were the first ones to put together observational data with mathematical theories.
That doesn't mean that in ancient Babylon or in ancient Egypt or anywhere else, there wasn't somebody scratching his head sometime, wondering, exactly why is this occurring, and engaging in the same kind of rational, critical thought. But it catches on with the Greeks, and it takes a mathematical form that we don't see elsewhere. To take geometric representations of the universe and use those to describe things in detail is really a departure.
One of the first Greeks to apply geometric thinking to the heavens was Aristotle.
He's really the founder of many fields, an enormous range of disciplines that he systematized, explained their methods, brought together the knowledge of his predecessors and his own original research and insights, for example, in ethics, physics, metaphysics, biology, psychology, logic, rhetoric, poetics. But Aristotle was not a mathematician, and that affects the way he did astronomy.
Aristotle viewed the universe as a gigantic sphere outside of which there was nothing. At the center of the sphere was the Earth. Each of the planets revolved through a complex set of spheres around the Earth. The sun as well and the moon, which were regarded as planets within Greek thinking. And then the stellar sphere at the outer part moved everything around it.
From the earliest times, the heavens were considered to be sacred and divine and most noble and worthy. The Earth and the sublunary world and humankind is the most vile and crass form of existence, subject to constant change, whereas the planets are the perfect bodies, noble, perfect, moving indefinitely in a circular motion.
With Aristotle's vision of the universe, Greek astronomers set out to predict the motion of these perfect spheres.
The ancient Greeks spent a lot of time looking at the sky, trying to observe the motions of the stars, the sun, the moon, and the planets, especially the planets. That was the most complicated motion. And their goal in doing this was to try to come up with some kind of a model that they could then use to predict what the sky would look like, where the sun, moon, stars, and planets would be at some particular point in the future. Really, no one person deserves credit for coming up with this concept, but we still give credit to a man named Ptolemy. We call this the Ptolemaic system in his honor.
You have to think of Ptolemy as a pivotal figure in antiquity. Never before had anyone put together a tremendous mathematical treatise that actually coped with the hard facts of observation. It was not quite like Euclid's geometry, in which you could have clean proofs and perfect figures. When you had to try to find the length of the year or the tilt of the Earth's axis, all of these things, they became ambiguous and hard to do.
Ptolemy had to make a system so complicated because the planets move in very complex ways. In particular, they seem to stop and even go backwards in the course of their cycle. For Mars, it's like every 2 years. For Mercury or Venus, it's up to every 4 months that the planet undergoes what are called stations and retrogradations, when it seems to come to a stop and then turn around backwards.
Now, this is a very peculiar phenomenon to try to explain, and Ptolemy did it very ingeniously by using a circle on a circle, what we call an epicycle riding on its deferent or carrying circle. And the combined motion would cause the planet to appear to move backward against the distant stars, and it would appear to move backward at the time when it was closest to the Earth and therefore brightest. But that wasn't nearly enough to work out the subtle details, because it could be shown that the planet Mars, on average, moves considerably faster on one side of the sky than on the opposite side. And Ptolemy arranged this by putting the carrying circle for Mars off-center from the Earth. But that still didn't work. It wasn't quite enough. It made the retrogressions just come out terribly. And so he invented another detail called an equant, another point of uniform motion within the orbit. And then the predictions came out really splendidly.
Now, this Ptolemaic model started with a fundamentally wrong assumption. Ptolemy, like most ancient Greeks, decided that the Earth was at the very center of the universe and that it was not moving at all. It wasn't spinning, it wasn't going around the sun, it was just sitting there. So the Ptolemaic model was not even close to describing reality, but like many models, like many intermediate steps in our quest to understand nature, it was still successful, and it satisfied their purpose of predicting the sky.
Greek astronomy was based on a fixed, unmoving Earth and a celestial sphere surrounding it, and in detail, that's wrong. But their astronomy survived, and it had a tremendous influence through the Middle Ages and into the Renaissance. People picked up that Greek model of the universe, and they saw that it explained what they saw. Their intuitive feeling for the way the sky looked matched exactly the Greek model of the universe. And then things began to happen.
When Nicholas Copernicus was a student in Krakow, that was exactly the time that Columbus was sailing to the New World. And at that time, everybody believed that the Earth was round, but that the Earth was solidly fixed in the middle of everything.
While Copernicus was a student at a university, he became acquainted with the revived controversy over whether the universe was Earth-centered or sun-centered. And Copernicus began to side with the idea that it was centered on the sun, that the Earth was doing the moving.
Copernicus had this wonderful vision in mind's eye that certain astronomical movements could be explained better by assuming that the Earth was spinning around, so that the apparent motion of the stars every 24 hours going around was caused by the motion of the Earth, and that similarly the Earth was also revolving around the sun.
I think it's possible he was motivated at least partly by aesthetics. A lot of people have this feeling that nature is very simple and elegant and beautiful, and if there are two ways to explain a phenomenon, a simple way or an easy way and a hard way, they figure that nature probably takes the easy way. Certainly, the Ptolemaic system is not simple. It was just covered with these epicycles, circles piled upon circles that were getting more and more cumbersome as people kept modifying it to try and get it to continue to give accurate results.
Because he felt that an astronomical model was not just a mathematical model, but a physical reality, Copernicus, in tinkering with Ptolemy, saw the enormous beauty of placing the sun at the center. The order of the planets became necessary. The planets took the longest in their cycles according to how far away they were from the sun.
Suddenly, retrograde motion was very easy to understand. It was really the big selling point for the Copernican theory. It was why many people began to think that Copernicus might be right. And we can understand how that works if we imagine the Earth and Mars, for example. Mars lies further from the sun than the Earth does, and Mars travels along its orbit more slowly. That means that the Earth overtakes Mars and passes Mars on the inside lane, like two race cars going around lanes. The car on the inside lane goes faster. As the Earth overtakes Mars and passes Mars on the inside lane, we look out from the Earth toward Mars, and we see Mars seeming to slow down, and in fact, seeming to move backwards.
It's really an illusion. The planets are always going in the same direction at a fairly constant speed, but as we pass them, they appear to go backwards relative to the distant stars.
Another advantage of the Copernican system is that it solves the problem of the motion of the fixed stars. In a geocentric system, the stars, which we all see in the sky, are believed to be fixed on a sphere which lies beyond all the planetary spheres, and therefore must move faster than all of them at very high speeds, which some believe to be rather ridiculous.
Copernicus provided an alternative to such notions in a book that would ultimately recast the order of the universe.
The full title is On the Revolutions of the Heavenly Spheres, and it is indeed a revolutionary book because it explains how you can understand the motions by putting the Earth as a moving platform and linking the motions of the planets all together in going around the sun.
Copernicus produced a very important book, but he refused to let it be published until he realized he was dying. And I think there's a number of reasons for that that are revealing. One thing you have to remember is that Ptolemy's version of Aristotle's universe survived for almost 2,000 years, and it was adopted by the church as official dogma. Their universe, with the Earth at the center, that geocentric universe, fit beautifully with the church's belief of hell at the center of the Earth and heaven at the starry sphere. Also, you have to remember that Copernicus was a member of the church from the age of about 10 years old. He was an official in the church, and I think he didn't want to embarrass the church.
In the preface, Copernicus makes sure to explain his allegiance to the church, his awareness that his theory is new and different, but he says that reform was necessary, and he really did this work in order to help the church in its goal of calendrical reform, and was always a faithful Catholic.
Although the work of Copernicus would eventually revolutionize astronomy, scholars of the day did not readily accept the premise of a moving Earth in a sun-centered universe.
The heliocentric system seemed completely absurd to the people at that time. For example, if you would have a bird flying up and the Earth is spinning around every 24 hours, I mean, bye-bye birdie. Throw up a stone, it would land in another county. So this seemed completely ridiculous.
This hypothesis turned out to be absolutely correct. The Earth does go around the sun, quite the contrary of what the ancients believed. But when Copernicus tried to build a new model based on this hypothesis, based on this presumption, and of course he wanted this model to be more accurate than the Ptolemaic one, he failed. He failed to prove his hypothesis as well, because unfortunately the Copernican model had other flaws in it. Like the Greeks, Copernicus believed that the only simple, elegant, beautiful motion that was possible in the universe was a perfect circle.
Because he kept the classical idea of uniform circular motion, his revolutionary idea didn't work, and in the end he couldn't calculate where the planets were. And I think he must have spent the last 10 years of his life really struggling, trying to prove that his revolutionary idea would work, and the mathematics didn't work out.
Almost 70 years after Copernicus, scholars still debated the idea of a sun-centered universe. Then a scientific innovator forever changed our view of the heavens.
I like to think that Galileo was one of the principal people who changed the rules of doing science. He desperately wanted to find a proof for the motion of the Earth. He said he couldn't admire enough those who had accepted the heliocentric system despite the evidence of their senses.
What really fundamentally changed astronomy was the use of telescopes for observing the heavens. Galileo was probably the first person to do this in late 1609, and what he saw quite amazed him.
He was ingenious enough to think not just of looking out into the Venetian harbor at the ships that might be about to arrive, but he turned it to the heavens, and he turned it to the moon, and he saw the pattern of light and shadows on the moon and began to realize that there were mountains, and then he could just barely discern the idea of craters.
These were very important for the new astronomy. For one thing, in Aristotle's cosmos, the heavens were perfect and unchanging. Nothing at all like the Earth. There was a completely different element, the fifth element, the quintessence made up the heavens. But when you look at the moon through a telescope, it kind of looked like the Earth. Yet, how could this be in Aristotle's universe?
It was a few weeks later that the real moment arrived, the moment of truth, as we might say. And that was after he had been looking at the planet Jupiter for several days. He saw that there were these little points of light around it, and he suddenly caught on that they must be satellites going around the planet.
That discovery would allow people to think that maybe the Earth is like Jupiter. It does have one satellite, the Moon. So the discovery of the satellites of Jupiter made it possible to think of the Earth as just a planet with a satellite.
One of the consequences of this is that it transformed what it meant to be an astronomer. That is to say, instead of charting the motions of planets which had been known since antiquity, Galileo now introduced new objects into the heavens.
One discovery of Galileo, one specific discovery of Galileo that was particularly damaging, and actually I would say a final refutation of Ptolemy, was the discovery of the phases of Venus. Because the phases of Venus cannot happen in the Ptolemaic system.
The phases of Venus, discovered by Galileo, were a real problem for the astronomers who believed that all the planets moved around the Earth.
When Galileo saw Venus move through phases, like the moon, he knew it must be circling the sun. In these observations, he found support for a Copernican universe, a position that contradicted the teachings of the Church.
Galileo got himself into deeper and deeper trouble with the Church, not heeding warnings that he received early on. In 1616, the Counter-Reformation Church, which was particularly fussy about adhering to conventional interpretations of the Bible, those of the Church Fathers, felt that Copernicanism could only be maintained as a hypothesis. In 1632, Galileo personally was summoned to retract the views that he had published in support of the Copernican theory in his dialogue concerning the two chief world systems. Pope Barberini, who had originally been Galileo's friend, felt that he'd been made a fool of and summoned Galileo to Rome, where he was forced to retract his belief in the Copernican system and to promise never to write about it again.
Even though the Church was able to suppress the views of Galileo, it did not hold sway in Northern Europe. There, astronomers were making observations that would unlock the secret of planetary motion.
Tycho Brahe was a Danish astronomer and an observer, and his particular brand of cosmology became very much honored during the 17th century as an alternative to Copernicus. He built wonderful instruments. This was before the time of the telescope. He pushed naked eye astronomy about as far as it could go.
Tycho was not a modest man. In his study, he had statues of all the major astronomers, and he included himself, of course, and even his son, young Tychonides, in anticipation of great works that never came. And he ran his own printing press, from which he would run off works describing the great instruments that he had devised.
Before 1609, all observations of the heavens had to be done without telescopes. If you made your instruments extremely large, very stable, and with a lot of metal parts that could be engraved, you could get very accurate observations. And in essence, Tycho Brahe, at his island of Fyn in the Danish Channel, had enough money, granted by the King of Denmark and his own family, to establish his own private observatory. He built a large number of important instruments, including the most famous one, the mural quadrant. This would be used to very accurately locate the positions of the planets and the stars in the sky.
He was precise down to 1 minute of arc, which was inconceivable until then, because his instruments were so large and they were made of metal, and they were finely gradated according to a system which he had devised himself.
Despite his advanced methods of observation, Tycho Brahe could not accept the revolutionary model of the universe proposed by Copernicus some 50 years earlier.
Tycho Brahe was not a Copernican. He believed firmly that the Earth had to be stationary, both for physical reasons, nothing as crass, as heavy, and as vile as the earth could possibly move like the noble heavenly bodies, and for scriptural reasons, that a number of passages in the Bible indicate quite clearly that one should take for granted the stability of the earth. Although he appreciated the beauty of the Copernican system, he wouldn't have anything with the motion of the earth and opted for a compromise known often as the Tychonic system or geoheliocentric system, which purports to provide the best of both.
So what astronomers like Tycho did was try to compromise and show that you could still have a geocentric universe in reality, but the planets could still move around the sun while the sun moved around the earth. And this was another way of looking at the universe, which also mimicked what you saw in the sky.
Tycho labored to reconcile this model of the universe with his meticulous observations and hired a young mathematician, Johannes Kepler, to work out the details.
Kepler knew of Tycho's work, and clearly these were the best observations imaginable. And he submitted to working with Tycho, who was probably a rather difficult person to get along with, in order to have access to this data. And indeed, on Tycho's death, Kepler was free to do with it as he chose, whereas Tycho had always insisted on using his data only to prove his own Tychonic system, which was a geoheliocentric one. Kepler turned it to the heliocentric system, which he had always believed in.
Johannes Kepler stands in a kind of divide between an ancient way of looking at things and dividing knowledge and our much more modern way of looking at things. You have to understand that at the time of Copernicus, people would have kept physics, the nature of the world, how it was made, in one bin, and astronomy, the mathematics of the movement of the heavens, in another bin. With Kepler, all of a sudden, these two become combined.
Kepler was motivated by the faith that God was a geometer and had created everything according to number, weight, and measure, as it said in the Bible, so that the order and the number, the size, the distance of the planets had to be there for a reason. Throughout his life, he felt deeply that there was a mathematical coherence and beauty to the world, which we could find with enough perseverance and hard work.
After years of struggling with Tycho's observational data, Kepler finally discovered this mathematical coherence in his 3 laws of planetary motion.
Kepler derived the first of his 3 laws through sheer hard work. He describes this in his commentaries on Mars or Astronomia Nova with amazing first-person verve. For 10 years, he tried to fit Tycho's data to a circular motion for Mars. And for 10 years, he failed.
There simply was no combination of circles that Kepler could use in his model and still get his model to match the observations of where Tycho actually saw the planets in the sky. And so he finally tried something that no one had ever done before. He considered an ellipse. And all of a sudden, everything fell into place perfectly. What Kepler finally discovered was that the planets, including the Earth, go around the sun. Copernicus was right about that. But they move in elliptical orbits, slightly flattened circles, with the sun slightly off-center. And as the planets move closer and farther from the sun, they also go faster and slower. And the amount of time it takes a planet to go around the sun once is related to how far it is from the sun on the average, by a very simple mathematical rule.
He was ecstatic when he found this because he felt that it pulled together so many of the other things that he had discovered. He put it in his book. He said, it can wait a century for a reader just as God has waited 6,000 years for a witness.
With Kepler's 3 laws, astronomers now held the mathematical tools to predict the motion of the planets, but had yet to determine why these motions occur.
Kepler had the right numbers and the right laws of the motions of the planet, but he had no theory to explain them and couldn't integrate the mathematics with a physical explanation.
His discoveries were simple conclusions based on Tycho's data. And even though they had a predictive ability in terms of knowing what the solar system would look like in the future, they could not be expanded to describe anything else, like how fast an apple falls to the ground, or how fast a ball will roll down a hill, depending on how steep the hill is, or how fast two stars will go in orbit around each other.
The work that began with Renaissance astronomers left many questions unanswered. Yet their efforts marked a turning point in how we perceive and attempt to explain the natural world.
It's difficult from our modern perspective to understand what an enormous change in categories of thought was being required to get from medieval science into modern science. For example, when Copernicus did his work, he was working as an astronomer, making mathematical models, but at the same time he was making a suggestion that, well, maybe this is a real way of looking at the cosmos quite differently. And that wasn't exactly what astronomers were supposed to be doing.
And I think it's understandable if you remember the way people thought about evidence at the time. Galileo and Tycho Brahe and Johannes Kepler weren't just making discoveries in astronomy. They were inventing science. They were inventing a way of seeing the world.
Forever after, science worked with trying to find the most coherent scheme, the way that things would hang together, not looking for specific detailed proofs of things, but rather an understanding of the cosmos that makes sense.